On behalf of Department of Mathematics, BK Birla College Kalyan, I welcome Professor Sudhir Ghorpade from IIT Bombay for joining this Theorem a Month lecture series. I also welcome and thank to our Director Dr. Naresh Chandra, Principal Dr. Avinash Patil for encouraging and supporting this activity. I welcome all the mathematics teachers, research scholars and students in this lecture series. The agenda behind this lecture series is to motivate UG and PG students to pursue mathematics and to inculcate research interest towards the subject. This year is our Golden Jubilee year. We are celebrating this year, and this year is also marked as our patron Pujya Shri BK Birla Babuji. It is a birth centenary year of our patron. So we are celebrating his birth centenary year as well as Golden Jubilee year of BK Birla College Kalyan. Theorem a Month is an idea of Professor Anuradha Garge, University of Mumbai, who constantly motivated and guided us to execute this activity. Till now, 12 professors from IIT, TIFR and reputed institute have delivered a talk in this series. We are delighted to have distinguished Professor Dr. Sudhir Ghorpade sir in this lecture series. I request my colleague Mr. Krishna Gode to introduce Ghorpade sir. Over to you, Krishna sir.
Thank you, sir. Good morning to the one and all present here. Today's guest speaker, Professor Sudhir Ghorpade sir, respected Director sir, Dr. Naresh Chandra, respected Principal sir, Dr. Avinash Patil, all the faculty members and student participants of BK Birla College, as well as faculties and students from various colleges. It's an honor for me to get the opportunity to introduce today's guest speaker, Professor Sudhir Ghorpade sir. Sir completed his BSc from University of Bombay in 1982, MSc from IIT Bombay in 1984, and PhD from Purdue University, USA, under the guidance of Professor Shriram Abhyankar. Sir was teaching assistant as well as research assistant in Purdue University from 1984 to 1989. And in 1989, sir joined IIT Bombay as a lecturer, and then till date, sir worked as assistant professor, associate professor, professor, head of the department, institute chair professor of IIT Bombay, and now sir is professor with higher administrative grade. Sir was also a visiting faculty in many national, international institutes, including institutes from France, Germany, USA, Denmark, etc. Sir is editor for many international journals. Sir was honored with many, more than 20 different grants and awards. Sir gave more than 400 invited talks in many national, international conferences, refresher courses in different institutes across India as well as outside of the country. Sir was an organizer for many national, international workshops, seminars, symposiums. Sir was members of American Mathematical Society, Mathematical Association of America, and currently Sir is member of Indian Mathematical Society, Ramanujan Mathematical Society, and the Mathematical Consortium. Sir has written around 6 books and around 50 research articles, which are published in international journals and having with around 1,000 citations. Under his guidance, 6 students were awarded PhD degree and 2 students awarded MPhil degree. So thank you, sir. Thank you so much for accepting our invitation and coming over for the guest lecture. Thank you. Thank you, everyone. Over to you, sir.
Thank you. Shall I start?
Yes, sir. Yes, sir.
Yeah, so first of all, I would like to thank Prakash, that is Professor Prakash Sansare, for inviting me. He had told me about this, and I thought this is a great idea that you have a series of lectures where somebody talks about one theorem a month, and I have seen some of the talks in this series, and they have been. I see that they have been very nice talks. So let's see my. I want to trying to share my screen. A little bit slow. maybe. Yeah. Okay. I think you can see my screen. Maybe I will.
Yes, sir. Yes.
Okay. So what I want to talk about is something called the spectral theorem, which I think many of you would have seen, even if you haven't, and a beautiful little problem of French mathematician Hadamard, which is often referred to as maximal determinant problem. Are you able to see and hear me well?
Yes, sir. We could see as well as we can.
One general caveat: if you have any questions, please either unmute yourself and ask. The point of using two devices is that you can also type things in the chat box. To the extent possible, I will monitor it. If I miss some chat, Prakash can tell me what the question or query is, and I'll be happy to answer that. Okay. So let's get started. Maybe some notation to begin with. In this talk, n will denote a positive integer. So I may not say it every time. I will write R n cross n, the set of all n cross n matrices with real entries. And you can identify it with the Euclidean space. If you like, Rn square. Okay, so this is like a, and okay, let us see if I want. Okay, so On is the set of all. There is an echo. Is it better now?
So you are muted.
Can you hear me?
Yes. Yes.
So we're back to the screen. Am I audible?
Yes, sir. You're audible.
So this is the set of all n cross n real orthogonal matrices. What that means is these are the set of, let's say, n cross n matrix over, such that P transpose is equal to P inverse. Okay. This is equivalent to saying P transpose is identity, or you can say P transpose P. It's actually enough to assume one of the things, or rows of P form an orthonormal set with respect to the usual dot product. That means the dot product of any two distinct rows is 0, and dot product of a row with itself is 1. And instead of row, you can take columns. So any one of these could be taken as the definition of this set On. Maybe I should give some examples. Simplest example is, of course, the identity matrix. That's an orthogonal matrix. Its inverse is itself, which is also H transpose. Another classic example is the so-called rotation matrix. So say cos theta, sin theta, minus sin theta,
There's some disturbances coming from your end.
Okay. Is it better? Hello?
And your voice is also low.
Is it better?
Yes, sir, it's better.
Yes,
Thank you. All right, so you can check very easily that the inverse is equal to the transpose. In fact, you know how you can invert 2 by 2 matrices. If you take 1 over the determinant, here determinant is cos square theta plus sin square theta, which is 1, and then you swap the diagonal entries and change the signs of the non-diagonal entries. So that's just exactly the transpose. So this is an orthogonal matrix. You can take, for example, for any.
So echoes is coming, sir. Sorry, but we could hear some constant noise in the background. Sir, we are not able to hear you. Hello. Yeah, but voice is little low.
So I will disconnect from one device and only connect from one of the devices. Okay?
Yeah, that will be great. That will be great.
So
Then it
hello, can you hear me now without the echo?
Yeah, sir, it is better now. Yeah.
Yeah. Okay. So basically now what is going to happen is I'm just using one device, which means you cannot see me, which is not much of a problem. I'm not much to look at. But then I cannot see or hear your chat. So if you want to ask some questions, please unmute and ask, or maybe Professor Prakash can transmit the question to me if something is typed in the chat box, because I will not have a way to see this. Okay?
Yes, sir. Yes.
Yeah. All right. So I can mix up the identity matrix and this rotation matrix. So for example, I could take identity up to some level. So and then I can put this rotation matrix somewhere. So cos theta, sin theta, and then again continue with identity, and then again maybe you have cos theta here, you have minus sin theta, and then you continue with the diagonal, and everything else is 0. So maybe this is the rth row, this is the sth row, and this is the rth column, and this is the sth column. So so maybe I call it PRS. Okay, so this is which is basically the identity matrix, except the entries in the position R, RS, SR, and SS are that of the rotation matrix cos theta, sin theta, minus sin theta, cos theta. Okay, so this is also n cross n orthogonal matrices, and you can check that. And you can get more examples. Maybe just I make one more observation. If let's say P and Q are orthogonal matrices, then so is P times Q. That's clear, because you know PQ inverse will be P and Q are invertible first of all, and PQ inverse will be Q inverse P inverse, which by definition is Q transpose P transpose. But then that is same as PQ transpose. So and of course if P is orthogonal, then so is P inverse. Okay, that's also clear. So another way of sort of saying that is that this ON forms a multiplicative group with respect to multiplication of matrices. Okay. So now what is this? What is this spectral theorem? There are, like any good theorem, you know, this has many avatars. So I'm going to focus on probably one of the most fundamental one for real symmetric matrices. So what this says is that every real symmetric matrix can be orthogonally diagonalized. Okay, I'll explain what that means. What that means is that suppose I have a real symmetric matrix, asymmetric. Then it implies that, let's say, Q transpose AQ is diagonal for some orthogonal matrix Q. Of course, Q transpose, because Q is orthogonal, Q transpose AQ is same thing as Q inverse AQ. So this is so you could say that A is similar to a diagonal matrix, but in a strong sense that the so to speak, the change of basis matrix is not just an invertible matrix, but an orthogonal matrix. So I hope this statement is clear. This is a very classical theorem. So this, I was sort of looking up a little bit of history. So this goes back at least to, Cauchy in 1829, who sort of wrote a paper where he showed eigenvalues of real symmetric matrices are real, and further went on to show that it can be orthogonally diagonalized. Somebody is interested in history, I can point out to you a nice article of Thomas Hawkins on this thing. Okay, so this is really, I would say, one of the high points of a standard course in linear algebra. I do not know if this is proved in your BSc course. Is this done in BSc? This theorem? Maybe it's the statement. Not the
Yes, sir. Yes, sir. It is done in BSc.
Oh, okay, wonderful. So if you have done that, and you remember the proof is rather involved. I mean, there are many ways you can do induction. You have to carefully find a basis of eigenvalues and then orthonormalize it. You will also use the fact that the characteristic polynomial will factor completely into linear factors. So that's sort of fundamental theorem of algebra. And then the eigenvalues are real, and you can find a basis of real eigenvectors, which is actually orthonormal. So on the other hand, so I'm going to present a proof which is due to Herb Will, and it sort of does this theorem in one shot, and I rather like it. Let me just remark. So this has many consequences. So, for example, once you prove that, it follows that eigenvalues of real symmetric matrices are real. Because after all, Q transpose Q is a real orthogonal matrix, A was a real symmetric matrix. So this diagonal matrix is going to be real, and the diagonal entries will be precisely the eigenvalues. And if you like, algebraic multiplicity is equal to geometric multiplicity. You can find an orthogonal, in fact, orthonormal basis of eigenvectors of the eigenvalues of the given real symmetric matrix, and so on. Okay, so so you can do all this. Another way to think about spectral theorem is I said that what did I say? Q transpose AQ is a diagonal matrix. So, and you can arrange the diagonal entries so that maybe whatever, suppose lambda 1 to maybe lambda t are the distinct eigenvalues. Lambda 1 comes certain number of times, maybe lambda 2 comes certain number of times, and so on. And maybe, I don't know, lambda t comes certain number of times. Okay, say maybe m1, m2, mt. These are the multiplicities. Then this diagonal matrix, you can kind of think of it as, let's say, lambda 1 I1 plus lambda 2 I2 plus lambda t it, where ij is the matrix where you have it's a diagonal matrix, and you just have 1, 1, 1 in the position where lambda j was, and 0 elsewhere. So if you think about it, ij is like the matrix of projection onto so ij corresponds to projection map, say maybe Rn to R, maybe something like Mj. Okay, where Mj is the multiplicity with which lambda j occurs. And now you can push this Q and Q transpose to the other side. Okay, so this will be then lambda 1, let me call it P1 plus lambda 2 P2 plus lambda T Pt, where what is this Pj? The Pj would be Qij transpose, and you should notice that this projection Ij is actually 0 if I is not equal to j, because you have 1 1 1 1 in different positions. So they are just two diagonal matrices. So they will be 0 if I is not equal to j. If I is equal to j, they will be well, it is just one getting multiplied. So if you like, it is delta Ij times Ii. Delta Ij is the Kronecker delta, and hence if I look at Pi Pj, you multiply by Q on the left, Q transpose on the right, and you can sort of push Q transpose between I and Ij. So this will also have the same property. This will be delta Ij Pi. Okay, so that means Pi Pj is 0 for I not equal to j, and Pi square is equal to Pi. So these are the mutually orthogonal projection matrices, if you like. So it is. I mean, I just so you can say that every real symmetric matrix can be written as a linear combination of these projection matrices. So in this form, the theorem has an extension, so extends to so-called bounded self-adjoint operators on Hilbert spaces. You don't have to know what that is. Historically, that was the extension of spectral theorem, which was worked out by von Neumann. And if you do your MSc, do a course in something what is called functional analysis, this will be one of the high points, spectral theorem, which is really an extension of the spectral theorem for real symmetric matrices. So, by the way, if you're interested in that kind of a thing, you can. There's a nice article of Halmos with which sort of says what does the spectral theorem say in the American Math Monthly. I can give a reference anyway. But I will be concerned with the more elementary part of the spectral theorem, which is this, that every real symmetric matrix can be orthogonally diagonalized. Okay, so let me begin by trying to give a proof. By will of the spectral theorem. So Will wrote a paper again in the American Mathematical Monthly, which is sort of called, which is really only one-page paper if you look at it. And here he outlines this proof, and since it does this non-trivial theorem in one shot, I thought it would be a good idea to present it. Maybe this is not so commonly known. So, so let me again begin with some notation, or if you like, definition. For any matrix A, n cross n real matrix, let us take. Let me give some name to the entries. For A equal to Aij, let ODA, OD stands for off diagonal, be summation Aij square, where I varies over all numbers between 1 and n, I not equal to j. Okay, so this is the sum of squares of the diagonal entries of A. So that's where that's what OD stands for. Okay. So so clearly this because it's a sum of squares of real numbers, this is greater than or equal to 0, and this is equal to 0 if and only if all the off diagonal entries are 0, which means if and only if A is a diagonal matrix. Right. So in some sense, finding a diagonal matrix is equivalent to finding a matrix for which this OD of that is 0. Okay, very good. Okay, so now what Wilp does? Okay, so maybe I can use a different color. So this. So he says that he proposes this lemma about really arbitrary symmetric matrices. So what does this lemma says? That if A is a real symmetric matrix n cross n, okay, and A is not a diagonal matrix. Should I write like that? Not a diagonal matrix. Maybe A is not a diagonal matrix, which means OD of A is strictly positive. Then it says that there exists an orthogonal matrix P such that if you look at this P transpose AP, okay, and look at its sum of squares of diagonal entries, that is strictly less than OD of A. Okay, so not being not a diagonal matrix means it is this OD of A is strictly positive. So you can, what it says that is that you can find a orthogonally similar matrix for which OD would be strictly smaller than that. Okay. So so now so I will prove this lemma. It's not too difficult, but I just want to point out that suppose you prove this lemma, so the proof of it will immediately imply the spectral theorem using this lemma. Okay, how would that happen? So let's see. So so what is the spectral theorem? It says that suppose I have a real symmetric matrix, then it can be orthogonally diagonalized. You can find an orthogonal matrix Q such that Q transpose AQ is diagonal. So now what I do is consider a map, let us say F sub A, from defined on orthogonal matrices and taking entries in all square matrices, in fact symmetrics defined by. So FA just sends orthogonal matrix Q to Q transpose AQ. Okay. Just note that if A is because A transpose is equal to A, so that will imply that Q transpose AQ. If I look at its transpose, that will be Q transpose A transpose and Q transpose transpose, which is Q, but A transpose. So in other words, if A is symmetric, is symmetric, and of course real. Okay. So now also note that what is this ON, the domain? So the ON is just the set of all Q, maybe, okay, let's say Qij in such that so that the rows are orthonormal. So if I sort of Q transpose A, so let's just Q transpose Q is identity. That means if I take the ijth entry of Q transpose, so that will be, let's say, Q transpose IK, so which will be, because it's transpose QKI and QKJ summation K going from 1 to N. That is delta Ij for all Ij from 1 to N. Right. So so in particular, this is sitting inside those Q which are N cross N matrices, so that if I take, for example, I is equal to J, then this will be summation Ki square. So in particular, so that will be 1. So in particular, I would have that, let's say, all the entries must have absolute value equal to 1. After all, the rows have norm 1. So the reason I'm saying it is because this makes it obvious that this is a bounded subset of this Rn cross N, and this condition. So this implies ON is bounded, and if I look at this, then that would imply that this ON is a closed set, because it is just defined by intersections of zeros of polynomial equations. So if you like, you have this these n square equations, and they're zero set, so that will clearly be a closed subset. So the point I want to make is that, and thus ON is a closed and bounded subset of this Rn cross N, if you like, this Euclidean space Rn square. What does that mean? You know that in the Euclidean space, that is a compact subset. Okay. Also, if I look at the map FA, what kind of a map that is? It's sort of taking Qij to whatever is the ijth entry of Q transpose AQ. So that A is a fixed real symmetric matrix. So again, that's sort of a polynomial in the Qij's. So F is clearly a continuous map. Is sort of a continuous map from ON, which is a subset of compact subset of Rn square, to Rn square. Okay. You can check that. There is really nothing. I mean, sort of, if you understand continuity and the basic results, this is obvious. So now your first year BSc calculus result kicks in. So if I have a continuous function on a compact subset, so now what am I going to do? So I'm just so let's see. So I have. So I have this ON going to maybe FA Rn square, and from Rn square I have this map which takes any matrices to the sum of squares of its diagonal matrices. Okay, so all right. Maybe before I even come to that, let me just say, because it's a continuous map, hence the image of that is a compact subset of Rn square. Okay, the image of this continuous function maps a compact set to a compact set. Continuous image of a compact set is compact. That's something we learn in BSc, also MSc, and so on. So you have that this guy is a compact set, and so the real valued function OD when restricted to this this compact subset must have a minimum. Okay. What does that mean? That means there exists some, so let me call it D, which is a FA of Q. Such that the off-diagonal entries of D are strictly are less than or equal to the off-diagonal entries of let us say B for all B in this compact set. Is it clear so far? Hello?
Yes, sir.
Yeah. It's good if you occasionally say something, somebody, because otherwise, if the connection is lost, I may not know it. All right. So now, so I claim that D is a diagonal matrix. Okay. If I show that, you see, then I'm done, because what is D? D is the image of Q. That means D, if you like. Okay, let me write it here. D. This is Q transpose AQ by definition. Right. So I would have shown that there exists some Q which is orthogonal, so that Q transpose AQ is diagonal, and that's precisely the spectral theorem. So so let's see, how do we show that? So okay. So you assume the contrary. Suppose not. Then what does that mean? It's not a diagonal matrix. That means OD of D is strictly positive. Okay. Now this is where I'm going to use this lemma of Wilp. Hence, by Wilp's lemma, there exists some P in ON such that the OD of P transpose A, sorry, not A, P transpose DP is strictly less than OD of D. Okay. But look, what kind of a matrix is P transpose DP? P transpose DP, what was D? That is P transpose. D was Q transpose AQ and then P. So this is obviously PQ transpose A, not PQ, sorry, QP. QP transpose A into QP. In other words, and QP is also orthogonal, because since both P and Q are orthogonal. Okay. So what does that mean? That means that this P transpose DP, maybe I'll write it on a new line. Thus, P transpose DP is like a image of FA under some orthogonal matrix, because it is some orthogonal matrix transpose times A times that orthogonal matrix, namely the orthogonal matrix QP. Okay. But then this obviously contradicts the minimality of OD of D in view of star, because what was the assumption? The assumption was that D is the minimum, right? So this OD has a minimum at D. Okay. The OD of D is less than or equal to OD of anything in the image. But now I have found something in the image, namely this, whose OD of that is strictly less than that. So that is obviously a contradiction. And why did that contradiction result? So, so this shows that D must be a diagonal matrix And that was our claim, right? The claim is proved. And moment consequently, Q transpose AQ is a diagonal matrix for some Q and so the spectral theorem is proved. Okay, so that's a rather quick proof of the spectral theorem modulo this lemma of will. Okay, so to really complete the proof, you will need to prove the lemma of will, and I will do that next. But let me pause and ask you if there are any questions or something what I've done so far is not clear. Okay. So what we did basically was to look at the map which sends Q to Q transpose AQ. This is a map defined on the compact subset ON. It's continuous, therefore its image is continuous. Therefore, if I now look compose it with the real valued function OD, so that OD will have a minimum at some point of the compact set, which is the image of F sub A. And now suppose the minimum is at D. And then we showed using Wilf's lemma that D has to be a diagonal matrix. So in particular, proves the existence of a diagonal matrix D, which is of the form Q transpose AQ. Okay, so that was the proof. Any questions? Anybody? Hello?
No, sir.
All right. So then let's go towards the proof.
Sir, hello.
Yeah. Yeah.
Yes. So is my voice clear?
Yes, I can hear you.
Okay. So maybe I'm missing something, but from the Wilf's lemma,
yeah.
Is it not like, can we not directly conclude that we have such? So can you go back? Back a page.
Yeah, this one.
So, yeah, this one. So if A is symmetric and it is not a diagonal matrix, then there exists a P such that the OD of P transpose AP is strictly less than OD of A.
Yeah.
So from this, can we argue that? So now we know that OD of P transpose AP is strictly less than OD of A, and OD of A is also some finite number n, positive number.
Yeah, positive real number.
Positive real number. So then, since let's say if P transpose A, this OD is also greater than 0, then you can again get a matrix Q, which will, and so on. You can go and ultimately end up getting some so that you get a matrix.
So that's a nice question. So what you are saying is that OD of A is positive, then I can find another symmetric matrix which is like P transpose AP, whose OD is even smaller. If that is not diagonal, I can find yet another symmetric matrix which is orthogonally similar to that, and hence to A, whose OD is even smaller. And I keep going.
These are real numbers.
And I guess you want to say until we get 0, but this may not happen. You know very well that you can find sequences of positive real numbers
now I get
which converge to 0, but we never attain the value 0.
Correct.
These are not integers, so these are real numbers.
I don't know how. Yeah, I was having that integer thing in mind, therefore the induction thing.
No. Real matrices, right?
Right.
So that's why we need a little bit of. Okay. So that's where compactness kind of helps us discretize things.
Right.
Very good. Yeah, thanks for your question. So let us now try to prove this Wilf's lemma. Okay. Very good. So let's just remind ourselves. What do we want to show? We want to show that suppose A is symmetric and non-diagonal. That means OD of A is positive. Then I want to show that OD of P transpose AP is strictly less than OD of A for some orthogonal matrix P. Okay, that's what we want to show. Okay, so let's do that. Okay, maybe it's a different shade of. So since OD of A is positive, we must have, and maybe I can even say, we must have, say, ARS is not equal to 0 for some RS between 1 and n with R not equal to S. Also, since A is symmetric, we may assume without loss of generality that R is strictly less than S. Because if R is not, because ARS will be same as ASR, right? If R is greater than S, then you just exchange the R and S. Okay, because the entries are same. So if one is non-zero, the other guy is also non-zero. Okay, so therefore I have some R S entry of A to be non-zero, and that is an off-diagonal entry. Okay, so now consider, did I call it? Consider this matrix, this orthogonal matrix whose example I gave you earlier, say PRS. Okay, what was that? That was this one certain number of times, then cos theta, and then sine theta, and then again 1, and then again cos theta, and then you have minus sine theta here, and then again 1, and so on. Okay, so this is the rth row, this is the sth row, this is the rth column, and this is the sth column. Okay, so so this is obviously this is an orthogonal matrix. Okay, so so let's look at so maybe if suppose I call it maybe did I call it PRS or QRS in my earlier? Forgot now. Oh, PRS. That's okay. So maybe I call it PIJ, where Pij is delta ij unless ij equal to, the missing entries will be RR, RS, SR, and SS, in which case Pijs are, when it is RR, it is cos theta, then sine theta, then what, minus sine theta, cos theta, respectively. Okay, let us just try to so look at PRS transpose A into PRS. Okay, what kind of a matrix this is? Okay, so so maybe if I want to look at so maybe I can call it B. Okay, so equal to, let's say, Bij. These are the ij entries. Okay, so note that A is symmetric, imply that B is symmetric because it is like P transpose AP, and if you take transpose of that, you'll get P transpose A transpose P, but A transpose is A, so that is same as P transpose AP, which is B. So B is certainly symmetric. Okay. Also, if I were to take Bij, okay, if I want to compare the ij entry of B, you can just check that the Bij, suppose I and J don't involve R or S. So if if ij are in 1 to n, but don't take the values r and s, then this P is as good as the identity matrix. So this Bij is obviously equal to Aij if ij, none of I or j is either r or s. Okay, so really speaking, and what about, let's say, BIR? So BIR would be equal to, so let us try to understand what is the defining property. B is this. So BIR, matrix multiplication, you understand. So if you like, that is the kth entry of the transpose into klth entry of A into L R entry of of this P. So in other words, this is, I can write it below. Please stop and ask if something is not clear. So this is like PKI AKL ELR summation over all K and L. Okay. So now let us look at maybe this QLR, PLR. Okay. What is this? So suppose I'm yeah. So this PLR, well, that's going to be 1 if L is equal to R, and if L is not equal to R, it is going to be 0 except when L is equal to S, right? So sorry, not 1. L is equal to R. So let's see. Let me. So this is going to be cos theta if L equal to R. If SR, which will be minus sine theta if L is equal to S, and 0 otherwise. Okay, so the only values of L which are really going to matter are the ones which are R or S. So suppose if L is equal to R, so what do I get? So this is then now the summation over K, PKI AK R, and then it is cos theta minus PKI AKS, and then it is minus sine theta. So I have already taken the minus sign out. Okay. So really speaking, now if you allow me, this PKI is common, so I'll just pull it out of the thing. So so it would be this. Okay. So now again look at this guy. What is this going to be? So well, this is just this is so if I is different from R and S, okay, then this is going to be what will it be? This will be this will be like the entries of the 1 if K equal to I and 0 otherwise, because we are not touching the RS where there is a change. So the whole thing will be, therefore this will be what? So K will have to be equal to I. So this is like AIR cos theta minus AIS sin theta. Okay. So that's the upshot. So BIR, maybe I'll write it here. BIR is equal to this. In a exactly similar way, this is just matrix multiplication. I leave it to you to check that BIS will be equal to AIR sin theta plus AIS cos theta. By the way, I should have said here, if I is not in R and S. Okay, so one of the coordinate is R, and the other guy is not. Again, if I is not in R and S. Okay. And in fact, because B is symmetric, I can even say not is this BIR. Okay, so let's just say BRI is equal to BIR is equal to this, and same way here. BSI is equal to BIS is this. Okay. So in particular, now just look at this expression and this expression. What am I interested in? I'm interested in the off-diagonal entries of B. So what have I found so far? If I and J don't belong to R and S, then they're same as Aij. So they're contributing same thing as what OD of A is. And now if I were to look at say BRI, maybe I can write because I was writing IR first. BIR square plus BIS square. Look here. Now it will be square of this guy. So plus square of this guy. So AIR square cos square theta minus 2 AIR AIS cos theta sin theta plus AIS sin square theta. Here also I will get AIR square sin square theta. So cos square plus sin square will be 1. So this will be just AIR square, and that will be again plus AIS square, and the mixed term minus 2 AIR AIS cos theta sin theta and plus 2 AIR AIS cos theta sin theta, that will cancel. So I get this. If I is different from R and S, and of course Bij square is same as Aij square if I and J are not in R and S. Okay. So what does it that leave me with? So it leaves me with sort of BRS. So okay. So let us try to understand that. So if you like, OD of B will be equal to same thing as OD of A, but OD of B will have BRS square, and OD of S will not have ARS square. So that's what this thing is. Okay, very good. And I'm sorry, you have to take the both RS and SR, so 2 times that, because so if I and J are both belong to R and S, so the possibilities are BRS or BSR. And so is this clear? Hello? Have I lost?
Yes, sir.
you?
Yes, sir.
Okay.
Yes, sir.
Okay. So now let us look at. So now let us look at BRS. By the way, Bill Finn's paper doesn't do any of this calculation. He says this is just standard. But just to make it things simpler, so what is this BRS? So that is the RS entry of P transpose AP. I mean, like PRS transpose AP, the PRS and the RS entry of that. Okay, so what is that? So that will be summation. P is so P RK transpose, if you like, AKL PLS. Okay, summation over K and L, going from 1 to N. Okay. So what is that? So that is like PKR. It's the same matrix multiplication formula, K and L. Okay. So again, as before, this PLS, we have seen what that is. This PLS is going to be, maybe I can write it if you like. So this PLS, that will be if L is equal to R. So now we're talking about the rth row. So that's minus sine theta if L is equal to R. L is equal to S, it's cos theta, and 0 otherwise. Whereas this guy, This is the rth column. So it will be, so rth column will be what? Cos theta if k equal to r, and and I guess minus sin theta if k is equal to s. I'm sorry, this is plus sin theta, right? Rth row, r is less than s, and 0 otherwise. Okay. So if you remember what those entries are, then the only terms which will survive are, so k is equal to r, so that will give me PRR, k is equal to r, ARL, and LS. But so basically, really speaking, if k has to be r or s and l has to be r or s. So so you would have PRS when I take l is equal to r plus no, sorry, plus P SR A S. Let us take l is equal to r again, then PRS plus P SR A S, and then take r in the first place, then PRS, and plus what will it be? I take k is equal to s. This is r, so s, and then l is also I take s, so PSS. Okay. All right. So let us just try to understand. So now PRR, that was cos theta sin theta. I'm sorry, I have taken l is equal to s, so I should write ARS here. Okay. Very good. So now PRR and PSR. So that is
AR.
Yeah, something is wrong.
It should be ARR, I guess.
AR.
Just right.
Oh yeah. Right. Thanks.
Yeah.
ARR. Very good. ARR. Yeah, ASR. And then maybe here ARS, but it doesn't matter. Oh, no. So what is it? I have taken SR. That's okay. All right. So what will it be? So if I PRR and PRS, so rth row, so that has cos theta sin theta. So this is ARR cos theta sin theta, and then where is PRR? So PSR is going to be sth row, rth column, so that's minus sin theta. So if I'm not mistaken, just check. This is times sin theta cos theta. And then this is ARS, that's just a mixed term, and that's PSR times PRS. So I will have ARS into PSR is what is P? Yeah, so that will be minus sin theta. PRS will be sin theta, and here. So what I want to say is that I get cos square theta minus sin square theta. Just check. ARS into cos square theta minus sin square theta. Is something wrong? I have taken okay. Yeah. I think one of them should be RS. Okay. So anyway, you can I mean, I took K is equal to R, L is equal to S. Then K equal to yeah. So let's take K equal to R, L equal to S. And K equal to R, L equal to S. So that is PSS. And then SR, and RS. Okay, I think that is correct. So PRS, that is sine theta equal to R. Equal to R, L is equal to S. And SR, and now K equal to S, L equal to R, K equal to S, L is equal to S. SR, yeah, this looks correct. So, so do you agree that this is ARS cos square theta minus sine square theta? Oops, excuse me. I meant to highlight this. Okay. Anyway, so what I want to say is, so what I want to say is the following. Okay. So, so what do I get? So I will get that this OD, okay, or maybe even before. So let me say this BRS is equal to ARR minus ASS sine theta cos theta plus ARS into cos square theta minus sine square theta. Okay. So the point I want to make is now so far I have not said anything about theta. So now I'm going to choose this theta. So let's say maybe I call it phi of theta. Say. So notice that if I put theta equal to 0, what would I get? Sin theta cos theta, that will be 0. Cos square theta will be 1. So I'll get here ARS. And if I took theta equal to maybe pi by 2, what would I get? Again, sin theta cos theta would be 0. Sin square theta would be 1. So I will get minus ARS. So the point is, and we assumed, remember, that ARS is not 0. Where was that? Yeah, we assumed that ARS is not 0. Okay. So the point is, these have different signs. And since phi is clearly continuous function of theta, and ARS is not equal to 0, by intermediate value theorem or intermediate value property, there exists some theta between 0 and pi by 2 such that phi of theta is equal to 0. So take theta to be this value. Then what will happen? Then BRS is 0, which is of course BSR. Okay. So now if I go back to this equation here, for a suitable choice of theta, I have found that BRS is 0. So what does that tell me? That tells me that hence OD of B is equal to OD of A minus 2 times ARS square. So now ARS is non-zero, so that is strictly less than OD of A. And of course, B is P transpose AP for some, in fact, for P equal to PRS, okay, which is in ON. Okay, so I found a matrix which is like P transpose AP, whose OD is strictly smaller than OD of the given non-diagonal matrix. So that is Wilp's lemma. So I hope this is clear. It's really just a trick about taking this, changing this A with this rotation about 2 of the axes in space. Really, that's what this is. You leave all except the R and S axis fixed, and you rotate the R S axis, that plane by angle theta, and that's an orthogonal matrix. And if you just look at that P transpose AP for that orthogonal matrix, for a suitable choice of theta, that will have off-diagonal entries strictly smaller than the sum of squares of off-diagonal entries of A. Okay. So, Prakash, how much time do I have? I mean,
Sir, you can take 10 minutes more, not an issue.
okay. So I'm, many things are very small in my mind. So, okay, now let me then very quickly can use a different color, maybe. Okay. So let me talk about this. At least say something about this Hadamard's determinant problem. Okay. So what is the problem? The problem is very simple. How large can it A be if is a n cross n real matrix with absolute value of Aij less than or equal to 1 for all ij. Okay. Suppose you take a matrix. So for example, if I take matrix 1, 1, 1, 1, then that determinant is 0. But if I take something little bit smarter, maybe 1 minus 1, 1, 1, that determinant is 2. And you can play with these matrices, and you can actually find that 2 is the maximum possible value of a matrix whose absolute values are less than or equal to 1. Okay. So first note that since dit A is linear in each of its entries, we can assume, we can restrict to those matrices such that the entries are plus 1 or minus 1. Why is that? See, for example, suppose I have some, how shall I say this? Suppose I have some determinant A, B, C, D. Okay. And suppose A is not 1. Okay, then I say I can always add or subtract. I can add something to make it 1, or I can add something to make it minus 1. So suppose I add some alpha to A. What will happen? This will be like the original determinant A, B, C, D, plus it will be alpha 0, C, D. So this is like alpha times D. Okay. So if D is greater than or equal to 0, we can take alpha greater than 0 such that A plus alpha is 1. Okay, and suppose this is delta, let us say. and this is maybe delta alpha, and then delta alpha will be greater than or equal to delta, because d is greater than or equal to 0, alpha is positive, and I just add whatever I need to add. Mod a is less equal 1 to make it 1. Whereas if this d, which in general will be some n minus 1 cross n minus 1 minor, then we can take alpha negative such that a plus alpha is minus 1. And again, the determinant doesn't decrease because alpha is negative, d is negative. So this will be greater than or equal to delta, in fact, strictly greater than delta. Okay. So in this way, we can make each entry to be +1 or -1 without decreasing the determinant. Okay. So therefore, you have this equivalent version of this Hadamard's problem. Is how large can determinant of A be if A is a square matrix with entries of A entries of A in +1 -1. Okay, so you take a plus or minus 1 matrix, and then how large can this determinant of A be? This is exactly equivalent to saying you can take a matrix with absolute value less than or equal to 1. How large can determinant of A be? So if you can find this, then you can find that. Okay. So so a priori it is not clear, what kind of a bound you would get and so on and so forth. So I just want to say quickly, since I have this Hadamard gave a beautiful bound. Okay, which says that let me say a plus or minus 1 matrix. That means entries plus or minus 1. Then the determinant of A, if you like, in absolute value, is always less than or equal to n to the power n over 2. Okay. So let me just try to explain how one can prove that using the spectral theorem. So this will be like an application of spectral theorem. Of course, you don't see a real symmetric. You see a real matrix, but you don't see a symmetric matrix. So you can do this standard trick. So let us take A here, plus or minus 1 matrix. So consider B to be A transpose B. Okay. So note that if I look at the determinant of B, that will be determinant of A square, and so whatever determinant of A is, that is greater than or equal to 0. And if I look at the diagonal entries of B, okay, so that will be like if I take that, it will be like taking the jth column of A transpose into jth column, which is like AJ. Okay, and AJ is the jth column. And because the entries are plus or minus 1, so their squares will be 1. So this will be 1 plus 1 plus 1 n times. In other words, this is equal to n. Okay, so all the diagonal entries are n, and hence, like the trace of B which is the sum of diagonal entries, will be n plus n plus n times, so that will be n square. Okay. So now, so where does the spectral theorem comes in? So by spectral theorem, Q transpose BQ is diagonal. Is, let's say, some lambda 1 to lambda n for some orthogonal matrix Q. Okay. And so I want to get an upper bound on determinant of A. So assume, without loss of generality, that determinant of A is not equal to 0. That is, which is equivalent to saying determinant of B is strictly positive. Okay. Then the lambdas are never 0. Okay. In fact, determinant of B is going to be lambda 1, lambda 2, lambda n, and trace of B will be going to be lambda 1 plus lambda 2 plus lambda n. And because trace of B was n square, so I get that the lambda 1 plus lambda 2 plus lambda n is n square. So now let's just see. So this determinant of B, that is lambda 1, lambda 2, lambda n, okay, which is like nth power of the nth root. So so I can I can just use the familiar AMGM inequality. So this will be less than or equal to lambda 1 plus lambda 2 plus lambda n divided by n, whole thing to the power n, because normally you would take the nth root to get the GM. So by AMGM inequality. But the lambda 1 plus lambda 2 plus lambda n I observed is n square. So that is n square upon n to the power n. So this is n to the power n. Okay. So I get that a determinant of A square is less than or equal to n to the n, and that implies that absolute value of determinant of A is less than or equal to n to the power n by 2. So that's a bound. This is called the Hadamard bound. And that's I just wanted to point out that that's a quick application of spectral theorem. The theory is very rich because the status of this determinant problem is that this is open in general. But what the bound will show that suppose there is a matrix for which this upper bound is met. Okay. Then obviously that will be the maximum value. So the matrices for which the bound is met, they're called Hadamard matrices. I think I will stop here. I've taken more time than probably I should have. So I thank you for your attention, and I welcome questions or comments if any.
Thank you very much, sir.
Yeah. Should I change exit screen?
Yes, sir.
Thank you very much, sir. I'm rather speaking. It was really a very nice lecture fitting into our theme, and it will be very nice if you could also give us few more references so that sometimes students can themselves lecture and teach each other some theorems every month. So
I'll be happy to
share
my notes and add some references there. Actually, one of the main reference I must say I have used is there is a very beautiful book which might be useful for your series. That book is called Proofs from the Book. Okay, I should explain what this is. There was a famous mathematician called Paul Erdos. So Paul Erdos had this belief that God maintains a personal book which has the best proofs of the best theorem, so to speak. Okay. So every time he would see a proof which is, which is so elegant and beautiful, he would say, this is from the book. Okay. And so there are people who sort of took that idea of Erdos and they collected a bunch of very beautiful proofs, and compiled it in various chapters, and use it in this book, which is called Proofs from the Book. I have a copy here. This is the book. You can see that.
Yes, sir.
It's edited by Eigner and Ziegler. So this Wilf's proof is there in this, and so you can say that it is from this God's personal book. Okay.
Yeah, so our director, Dr. Naresh Chandra, has joined. Just ask sir to give his remark.
Prakash Sansare, please
Yeah.
go ahead. This is more important.
Yes,
I'm
sir.
also enjoying
Yeah,
God's
sir.
book, particular book.
Yeah, thank you so much, sir, for joining.
So you go ahead with the program,
Yeah.
and go on.
Yeah, yes, we are done. I mean, of course, there are. I'm happy to answer questions, Professor Naresh Chandra.
Yeah, go ahead. All my best wishes.
Thank you. Sir is traveling, and despite of his busy schedule, he has joined. Thank you so much, sir. Student, if you have any doubt, you can unmute and you can ask your doubt, or otherwise you can post to the chat box.
If I may ask, actually plus minus 1 is just the cyclic group of order 2.
Yeah.
So is there a generalization of this to other groups, and are there bounds known?
I don't know offhand. Is Anuradha, is it?
Yes, sir. Yes.
Yeah.
Sir.
So see, the thing is that yeah. No, I guess I don't. I mean, there is this Birkhoff-von Neumann theorem, but so offhand I don't know some good bounds if you were to replace that by some arbitrary group. But this Hadamard thing is quite well known. I mean, see, the thing is that the construction of Hadamard matrices itself is another fascinating topic. If I had time, I would have said something about that. Because that means Hadamard matrix means a matrix for which the bound is attained. So those plus or minus 1 matrix for which determinant of A is exactly equal to n to the power n by 2. And it's not so difficult to show that if that happens, n has to be, and suppose n is bigger than 2, then n has to be divisible by 4. But then is every divisor of 4 for which there exists a Hadamard matrix? That's actually open. You know it for several values of n, like powers of 2, for example, but not every multiple of 4. Yeah, I mean, I have not answered your original question because, as I said, I don't know offhand whether similar bound exists for an arbitrary group. There might be some.
Yeah, may I ask something?
Yeah, sure.
This n raised to n by 2 is nothing but number of distinct label trees using Cayley's theorem. And the A will be the adjacency matrix, and I think it satisfies your conditions of plus 1, 0, 1.
Yeah. Well, that is usually 0, 1, no?
Yeah. So that connections can be said.
Yeah, I mean, you can. Yeah, I guess you can say something, but I'm not sure if if an adjacency matrix by itself, because would attain
because that will satisfy your symmetric condition and undirected graph. So diagonal entries will be 0, and elsewhere if there is adjacency it will be 1.
Yes. So what is the
no, since you had that bound less than or equal to n raised to n by 2, and Cayley's theorem says that about the.
That is true. So yeah,
that's why I thought.
Maybe there is a proof. I have not seen it myself, but I mean, yeah, that it's true that of course that n raised to n by 2 does appear in graph theory exactly the way you mentioned. So there may well be a proof along that. But here I just wanted to illustrate this as a application of spectral theorem from which.
No, it's okay. I just thought it's okay.
Yeah, thanks, Sanjay.
Yeah. Thank you so much, sir. I just request our mathematics faculty to kindly switch on the camera for a group photo. I request our director, sir, Anuradha Madam also, to kindly switch on the camera for group photo. Thank you so much. Anuradha Sanjeevani Madam, you can also on the camera.
We are in the college. So.
Yeah. Thank you, sir. Thank you, sir. Yeah, I request Gajanan Dumal sir to kindly. Okay, so there was some connection issue. So on behalf of K Birla College Kalyan, I extend my sincere gratitude and thanks to Professor Sudhir for joining this lecture and this wonderful lecture. I thanks all the faculty members for joining this lecture. My thanks are due to our director, principal for this joining this lecture. I also thanks Dr. Anuradha Madam, Sanjeevani Madam for joining this lecture. Hoping forward the same cooperation in future too, sir. Thank you so much.
Thank you. Thank you.
Thank you, sir. Yeah, participants are requested to kindly fill up the feedback form. Yeah. Thank you, sir.
All right. Bye.
Bye-bye, sir.
Bye. Bye, sir. Take care.